Hello everyone, my name is Alistair Duffy. I'm President of the IEEE EMC Society and a Professor of Electromagnetics at the Montfort University in the UK. What I'd like to talk to you about today is EMC and the climate emergency. I've got four guiding principles. Climate change is real and a global emergency. Society's use of energy continues to increase. Digital and communications technologies are on the rise and will continue to be on the rise for a considerable time. And the pivotal issue is that EMC and signal integrity, power integrity engineers are making considerable contributions to tackling the underpinning issues, but we don't often recognise that. I was having a conversation very recently with some colleagues, and our conversation was about the COP meeting coming up in Glasgow in November. And what is it, if anything, really, that EMC engineers contribute to tackling the climate emergency? And it was an interesting conversation. We weren't really quite sure whether we had a pivotal role, a role on the side somewhere, or really didn't have anything much to do with it. And that set me thinking about what it is we actually do relative to the three issues at the start of this list. And I realized actually that there's a considerable amount that EMC engineers and signal integrity, power integrity engineers do that actually allows the fight against climate change to happen. So really, this is as much a call out, if you like, to EMC engineers, to you in the APEMC audience, to look more at your contributions as it is about just information to a general audience. I'm going to concentrate on the fourth point in that list, but in order to get there, what we really need to do is to spend some time on those first three points. So what I've called principle number one for this talk: climate change is real and a global emergency. So where are we now? You'll see there's a URL down there from the United Nations. And I'm quoting directly from this particular link. So after a century and a half of industrialization, deforestation, and large-scale agriculture, quantities of greenhouse gases in the atmosphere have risen to record levels not seen in 3 million years. There are some links that they're making there that greenhouse gases in the Earth's atmosphere is directly linked to average global temperature on Earth. That concentration has been rising steadily, and therefore the mean global temperature has as well. And it's been noticeable since the time of the Industrial Revolution. And carbon dioxide is the most abundant greenhouse gas, and that's largely the product of burning fossil fuels. So if we look at the change in average maximum temperature from 2010 to 2019, compared with the couple of decades or so before, you can certainly see that there are significant areas that are 1.5 to 2 degrees higher than they were. Very few places, perhaps a few dots on the map, are colder. This is from bbc.co.uk. Again, the links for these images are in the talk, so should you want to go and actually have a look at the source that I've got them from, please follow the links. And linked with that, the number of days above 50 degrees centigrade has increased in each decade since 1980. So from 1980 to 2009, about 14 days a year, rising to 26 days a year in the decade above. The The Associate Director of the Environmental Change Institute at the University of Oxford says the increase could be 100% attributed to the burning of fossil fuels. So the practical upshot is that mean global temperatures will continue to rise well above the pre-industrial level. That's going to affect ice, and ice melt will continue with the resultant rise in sea level. And there are a number of models for this. Again, this is from the UN. Somewhere between 24 to 30 centimetres by 2065, increasing, of course, beyond that. And that's all relevant, so relative to the reference period of 86 to 2005 in this study. And most aspects of climate change will persist for many centuries, even if emissions are stopped. So, having really wanted to come to Bali for a number of reasons. One, because this is or would have been the first real meeting that I've been able to come to for some time. And also having an old school friend who lives in Bali, who regularly posts on social media some fantastic photos. It looks like a wonderful place to visit as well. However, as I can't come this year, what will happen in a few years' time if we recite the conference in Bali? Well, this is where I believe we are for the conference now. The resort's there on the right, and according to Climate Central, that will be a beachfront or possibly a seaward hotel sometime in 2050 and beyond. So if we're going to have sea level rising like that, if we have global temperatures rising, the effect of that is people will have to move. So the International Organization for Migration has done some studies. The numbers are difficult to predict, and they're predicting somewhere between 25 million to 1,000 million environmental migrants by 2050. The figure that they feel most comfortable with is about 200 million. And this is to round about 2050, again, sort of give or take time. But let's put that into context. If we look at the number of refugees, and apologies for the spelling mistake there, of course, displaced by World War II, Syria, Israeli-Palestinian conflict, Korean War, Iraq, Vietnam, the former Yugoslavian conflict, Afghan, Rwanda, Somalia, Central African Republic, Sudan, South Sudan, Democratic Republic of Congo, and Myanmar, we have a total of round about 100 million refugees. So about half of what we might expect with the most likely scenario with the current passage of global warming. Obviously, there's a high tolerance there, but it certainly indicates that there's the real emergency part of this climate emergency from the human side of things. And of course, as I'm a member of one of the IEEE societies, a member of the IEEE, we can return back to the IEEE's mission statement to show how that compels us as engineers to be part of the solution. The IEEE's core purpose is to foster technological innovation and excellence for the benefit of humanity. So on to that second principle. The use of energy continues to increase. And of course, energy use increases, but your energy efficiency also increases. So we'll just look at that. Now, forecasting the future of energy demand is very much a sort of crystal ball gazing exercise. There are many variables and facets And what I'm not going to do is to provide a meta-analysis here. I'm just going to take two organisations' views of the future, because there are some similarities, but there are also some variations in there, so you can get an idea of a potential range of what's likely to happen. So the World Energy Council was formed in 1923, and it aims to promote sustainable supply and use of energy for the greatest benefit of all people. And DNV, who've produced a number of reports, large multinational, and who say that since 1864, their purpose has been to safeguard life, property, and the environment, and their visions to be a trusted voice to tackle global transformations. Now, what I'm not doing is promoting these two studies over other studies. They're just helpful and convenient studies for this talk. So please feel free to go and have a look at other studies and analyses that could be useful and helpful. So the World Energy Council bases their predictions on two scenarios, jazz and symphony. And I'm paraphrasing here considerably about the basis of these scenarios, so I hope I'm not going to get into trouble from them. But jazz effectively is consumer pull with a relatively low governmental regulation. Symphony has more government intervention. And they're taking a base use of 546 exajoules in 2010. And they're predicting a rise of 61% by 2050 in the jazz scenario, the consumer pull, and a 27% increase in the symphony scenario. So 879 exajoules and 696 exajoules, respectively. DNV take a slightly different view, but I guess it's closer to symphony, and the principles do include quite a bit more governmental and international regulation. But their study is quite interesting because of the breakdown in energy sources. So we can see here where we are. This is the 2019 base, but you can see here that coal is declining, oil's declining, natural gas doesn't decline hugely to 2050, but they're still significant sources of power. Geothermal is a small but notable source of power here, as is bioenergy. Hydropower doesn't change an awful lot. Solar increases quite a bit from where we are at the moment, and so does wind power. The total numbers are not too dissimilar from the World Energy Council's, bearing in mind that they were looking at a 2010 baseline rather than a 2019 or 2020 baseline. So, having looked at that, the energy mix is going to go to, according to the World Energy Council, to about 77% or 59% in 2050. Nuclear, about 4% with the consumer pool, or 11% or thereabouts with the symphony model, and renewables increasing to 20% with jazz or 30% with symphony. So the greater regulatory support that's given to the market, the greater the use of renewables will be. DNV takes that fossil fuel share down to perhaps below the World Energy Council's, about 50% in 2050, with renewables going up to about 45%, nuclear being a fairly stable 5%. So fossil fuels are still significant. Renewables, though, have a substantial growth. One thing that we need to also consider is energy intensity. And this is a measure of how intensively energy is used, and it's a measure of energy consumption per GDP. It's actually been falling typically by 1.5 to 2% per annum over recent years. The World Energy Council sees a 50% reduction there and thereabouts in both models up to about 2050. DNV sees something similar. So the energy efficiency, if you like, is improving significantly. So some takeaways from this particular segment of the talk is predictions vary, as you might expect, about energy growth. But they're broadly in agreement about fossil fuels still being a significant contributor to the energy mix in 2050. And renewables are growing to the state of doubling or possibly tripling by 2050. I put in their brackets because of the JAS scenario, except in the case of weak international governmental climate leadership. And predictions agree that energy intensity is going to reduce by about 50%. So where will the energy be used? Well, it does seem quite reasonable that we'll continue to use it in industry, commerce, and the homes. But of course, what about transport? As a new electric car owner, I seem to be seeing more electric vehicles on the road. Now, whether that's just because I'm more aware of them or because there are more registrations, I'm not sure. I believe there are significantly more registrations. I think they're up quite a bit, certainly in the UK, in the last year. But do we really expect to see mass electrification a reality, or are we still going to be reliant on fossil fuels for transport? The EIA predicts the use of energy in this way, and they're using quadrillion British thermal units. I believe that's a convenient unit to compare energy. And I think just recently, one quad was about the daily consumption on the planet for energy. We can see here that transportation from the last, or from when this study was published, is growing significantly. So from whatever, that's sort of between 1 and 2 quads, up to nearly 10 quads in the coming 30 years. And the ICCT shows us something quite interesting here in the way that they believe that their vision of energy use will happen. And this is, as they say, an ambitious but feasible scenario. So we can see that as we go from the left to the right, our baseline energy will be added to with vehicle growth, the LDV, HDV growth, you can see there, growth in aviation, some marine growth, and some additional black carbon growth. However, with the use of zero emission vehicle improvements, compliance improvements, and significant work on efficiency and emissions improvements, we can see that vehicles will drop much of that growth down to perhaps below where that baseline is now. Marine and aviation improvements, while not significant for zero emissions, work on energy efficiency is going to make a big difference. So improving the efficiency of the vehicles will make a big difference. And as we can go along that chart there, we still see that there's a gap needed, or there's a gap to be filled rather, between the likely emissions with future policies and where we need to get to limit the climate change to a 1.5 degree rise. So on to principle 3, the use of digital and communications technologies continues to increase. This was a February headline in the BBC Online. Bitcoin consumes more electricity than Argentina. And the article was about the use of the data centers for mining cryptocurrencies and the amount of energy that they use. It did have some balance there, though. It did point out that some of the computing facilities were sited near renewable sources, such as hydro sources, and there's some innovation there in the way that energy was created. But nevertheless, this headline here that cryptocurrencies require so much energy to produce is quite a sobering thought. So having mentioned data centers, let's just have a little look at data centers. In 2018, they used about 1% of the global energy use. And they emitted about as much carbon dioxide as the commercial airline industry. Growth predictions to 2013 are up to 1.1 petawatt hours to 8 petawatt hours. But there are some energy efficiency strategies that are being used here. Artificial intelligence is already being used to predict cooling needs for some of the big data centers for, I believe it's Google that's doing this. Finland, I understand, it has quite a good trade in hyperscale data centers because obviously in a colder climate, less cooling or less forced cooling is needed. The use of renewables is an important strategy. As I mentioned before, some of the computing facilities used to mine cryptocurrencies are being sited in facilities where they can actually generate local electricity. And of course, things like heat recovery for use from other sectors is also a key energy efficiency strategy, so that that energy isn't wasted, it's simply recycled somewhere. And that comes from energypost.eu. The URL is there. And the paper here in Applied Energy, usage impact on data center electricity needs, a system dynamic forecasting model, looks at some of the data, and their figure 7 predicts from this terawatt hours down here on the bottom left, a number of scenarios by only 2030. So some of the talk I've talked about 2050, but this is just going up to 2030. So in the best case, we are seeing perhaps a doubling of energy use. In the expected case, we're seeing it going up nearly 5 times, and there's some confidence limits there taking us up to 1200 terawatt hours by 2030. So there's some clear expectation there that a lot of energy will be going into the data centers. And of course, things like IoT and mobile communication is going to require heavier use of these data centers. And this graph from Schneider, or this graphic from Schneider Electric, gives us a nice view here about where the energy in these data centers goes. So IT equipment is using just under half, and then we have just over a third or there and thereabouts used for cooling, and about 15% or thereabouts, 12 to 15% being used for just the electric support, sort of the power supplies, etc., lighting and auxiliary devices. This figure in the middle, PUE, the power usage efficiency, is just a measure of how much power into the data center is consumed by the IT. So it's another energy efficiency metric. So anything that we can do to improve the power efficiency or the energy efficiency of the IT equipment will help reduce that middle bit of the energy use in the data center. Reducing, of course, the cooling requirements will also have a big effect. So anything that we can do, anything that can be done, will be work well done, particularly looking at the predicted usage here. Okay, so let's move on to what we are doing as a profession to tackling the underpinning issues. So no doubt some people perhaps in this audience are working directly on renewables or on energy efficiency for data centers. But in far more cases, the work that is being done is more of an enabler, and that provides us with some support to allow some of those big changes that need to happen. So I'm just going to look at some examples over the next few slides. It's certainly not exhaustive, and there's no particular constructed narrative here. I just really wanted to provide some views of the subject. So perhaps during the rest of the conference, you can have a look at some of the work that's being undertaken and some of the research and the case studies that are being published, and think about how they actually do support this battling of the climate emergency. And the takeaway message really, and the thing that I want to try to get over with this, is that you and the rest of the profession are making substantial contributions to these enabling technologies. So thinking about the data center example there, when I talked about the importance of making the IT more efficient, then clearly, improving that energy efficiency of integrated circuits and the supporting electronics is a major design consideration. And one specific example of that, of course, is the power use, as I mentioned. And if we just take something as simple as CMOS technology, just to look at how we can contribute to this, we've got static and dynamic power consumption. Static consumption is leakage current times the supply voltage. The dynamic power consumption is the capacitance times the clock frequency times the number of bits times the square of the supply voltage. So reducing that supply voltage is a key element in reducing that power consumption. Of course, managing or reducing the power, the supply voltage, as we said, means that making stable power supplies and increasing the stability of power supplies with lower voltages and lower differentials between power planes is, of course, increasingly challenging as we start switching things faster, and we have, of course, those lower power supply voltages. So I've just got a handful of examples, really more in terms of paper titles, mostly from the recent EMC and EMC Europe joint symposium. So we've got machine learning based Verilog A modeling for supply induced jitter sensitivity for high speed memory interface. So looking to optimize the floor plan of the die package and circuit board, taking into account timing budget calculations. We have the power distribution network decoupling capacitors for EMI reduction based on deep reinforcement learning of the optimization of those. And if we just look at the EMC magazine, systematic power integrity analysis based on inductance decomposition in a multi-layer PCB power distribution network. So we have just 3 papers there, largely taken at random, that all contribute to the improvement of the power supplies. And as you can see, as you can trace back, if we can reduce the power consumption of an integrated circuit, we can reduce the power consumption of the data center, and we can see how that can track back to reduced energy usage and improved energy intensity. We look at vehicles. We saw the projected increase in the electric drivetrains. If we remember that graph from a few slides ago, looking to increase by, was it 4 to 5 times? So in order to be able to achieve this, and therefore, as we say, track back to the greenhouse gas emissions, work needs to be done. Power inverters, high voltage bus, charging, of course. And all these things are topics that are regularly discussed in the transactions and at conferences. Automobiles and other more electric vehicles are more data and communications dense. Such things as collision avoidance, tire pressure monitoring, entertainment system enhancements, all these things just require more data and more functionally safe environments. So the question, there is how much EMC engineering has enabled this evolution, or is it actually a revolution? Just again, taking some papers, this time from the transactions. This year, I've simply looked at one issue just to see what was there, and to check that my assumption that there is actually quite a bit of work going on is true, and up pops these 2 papers in issue 3 of the transactions. Safety evaluation of medical implants in the human body for a wireless power transfer system in an electric vehicle, and modelling and suppression of electromagnetic interference noise on the motor resolver of an electric vehicle. We have some more here from issue 1 and issue 4 of 2020. Impact analysis of electric fast transients on FlexRay in vehicle networks. Safety standard compliance of human exposure from vehicle cables using coupling factors in the frequency range of 0.3 to 400 kilohertz. Experimental evaluation of layered DD coil structures in wireless power transfer systems. So there's a lot going on there that is actually making an impact. If we look at energy security, a power system's capability to withstand disturbances, minimal service disruption. It's a significant part of policy action areas in any country. And some interesting facts, or at least an interesting fact, is about 85 or more than 85% of equipment failures are actually due to insulation failures. And these are often related to things like partial discharge events. And of course, partial discharge events are the, if you like, localized arcing in a dielectric, in an insulator, when the field strength rises above what can be supported by that dielectric. And of course, principally, these come about because of inhomogeneities in the dielectric, things like oil or gas or powder bubbles in there. A partial discharge event can make things worse, and then of course it becomes a self-perpetuating problem, that the partial discharge damages the insulation more. That damaged insulation becomes more susceptible to further partial discharge, and so we can then end up with this this runaway problem, which can lead to insulation breakdown. But of course, knowledge of possible problems can help the timely intervention and avoid energy outages and the emergency work that might have to happen to overcome those. And so some work that we've been looking at is partial discharge location using electromagnetic time reversal. So on the left, we've got just a simple illustration of a cable with a partial discharge source and the discharge propagating left and right with an observation point there. On the right-hand side, it's just an indication here that we've got a number of guest partial discharge locations. So we're looking to see where the observation point, if we run time backwards, will give rise to something that represents that partial discharge. So the EMIT project is a Marie Curie project with my research fellow, Dr. Antonella Ragusa, is working on. It's funded by, as I say, the EU Marie Curie project. And so on the left-hand side here, we've got a measured partial discharge signal. If we reverse that, we can then get the probable location of the partial discharge. The partial discharge was located at 613 meters in this particular example. You can see from the peak on the graph on the right-hand side that it's there and thereabouts, and the error is actually something under 1%. Of course, one of the big issues we've got is, well, how do we actually manage designing for and working with these predicted changes? Perhaps one of the key standards that helps us here is the IEEE standard 1848, which is just published last year. It's a standard for techniques and measurements to manage functional safety and other risks with regard to electromagnetic disturbances. Techniques and measures is what we usually say. And that energy security is just one example of determining and managing the risk. I'd like to thank Keith Armstrong. I apologise to him for the end of his name being cut off there in that graphic. But Keith Armstrong has been the prime mover for this work over many years, and it's ongoing in a number of sectors. And our technical committee 1, EMC management, is championing this work. So, okay, so what's functional safety? Well, it's the part of the overall safety that depends on the correct functioning of electrical, electronic, programmable electronic safety-related systems and other risk reduction measures. It's important to note there that the correct functioning of digital systems is important. And of course, sources of risk come from that electromagnetic environment changing over time. You know, we saw in some of the papers that I'd identified in a previous slide talking about the electromagnetic environment in a car. Clearly, that's changing with the charging and the increased information and entertainment technologies. Of course, things like semiconductor junctions age. So in 5 or 10 years' time, they may very well not be performing in the same way they did when they were made or designed. And the other problem that we do have, and a big issue here, is that testing the all combinations of all inputs for a digital system is impossible. So even with just something as simple as a 4 by 8-bit input and 16 binary inputs, we've got 2 to the 41 possible states. So even if we tested one state per 100 nanoseconds, that's 2.3 days of continuous testing. And I'm struggling to think of a real system that would be quite that simple. But the the important point there is that digital systems are non-linear. We could test 2 to the 41 minus 1 states in that example there, and everything works okay, but it tells us nothing about that final state. So we can't make inference there that we've tested some, so the rest will be okay. The other source of risk is repairs or changes may not return a system to the original state. And we mustn't forget, I put down here user error, but it may not just be error, just maybe that the equipment's not being used quite in the same way that it was designed to be used. And to give you just an example, a very quick example, some work that we did with York University of York, some time ago. We just looked at a number of circuits with some RF pickups designed onto the circuit, just co-located. And this was a microcontroller, switch mode power supply, audio amplifier. And we wanted to look at just what happens with the aging of semiconductor junctions. So we're simple circuits here, and you can see down at the bottom there, marked A, B, and D, but the top, the electromagnetic pickups. You can see them there in a bit more detail. So the systems were aged. Thermal cycling, the oven was operated at 140, which meant that the junction temperatures were going up to about 220, and full treatment was 2 cycles of about 1 week each. So there we are, devices in the oven being baked. And this is our reference system. So the red and the blue dashed line are baseline. The green dash and the yellow dot dash are after accelerated aging. This is a reference system. So I shouldn't have said accelerated aging. This is with avoiding the accelerated aging, but it's still some time on as a reference. If we then look at the aged system, we do have some frequency shifts here in the emissions. So those risks that I mentioned 3 or 4 slides ago are too complex to test for a priori. So 1848 presents the techniques and measures to specify the requirements, look at the design and the verification of those designs. And the aim is to ensure that errors, malfunctions, or faults in signals, data control, and power supplies are, where possible, avoided and detected. Once detected, they're corrected if possible, and if not, then switching to some form of safe state. The important phrase here is design confidence. The need for this is to ensure that the appropriate level of design confidence is presented. So that is potentially quite an important standard for us, and quite an important standard that we can use with derivative daughter standards for a number of more specific environments. So with that, I need to leave you with just some parting thoughts. Do we normally think of our community as enabling the fight against the climate emergency? I'm not sure that we generally do, but these few, and largely random, because there's so, actually looking into it, there's so much to choose from, and so much contribution that's being made. It's either we look at a specific sort of niche area or limited area and go deep, or we just take a few topical elements from around our publication landscape, just to show how our community is enabling this response. We should recognise these contributions, and we should be ready to tell others about what it is that we're doing in our community to help their communities fight the climate emergency. So with that, I'd just like to say thank you very much. And I'd like to wish you all the best, and wish you well for an informative and enjoyable conference. And I hope that I'll be there in person next year. Thank you very much.